Welcome to the deep dive. Today, we're really digging into a landmark paper. It's the one that kind of kicked off the modern era of AI as we know it. Attention is all you need from 2017.
Yeah, it's hard to overstate the impact. This wasn't just another paper. It was like a fundamental shift, a real break from what everyone was doing.
Absolutely. Before this, if you were doing anything with sequences, translation, summarization, you name it, you were probably using recurrent neural networks, RNNs, LSTMs, GRUs.
Right, those are the go-to models, but they were complex,
Mhm.
intricate, kind of computationally intensive.
And this paper comes along and the title just says it all, doesn't it?
Mhm.
Attention is all you need. They essentially said, look, we're ditching all that sequential processing. No more recurrence, no convolutions even.
We're building this thing just using attention. That was the radical idea.
And they didn't just propose it, they showed it worked dramatically.
The results were, well, stunning. Machine translation was the big test case on the standard WMT 2014 English to German benchmark.
Yeah.
They hit 28.4 BLEU, which, sounds like a number, but it blew past the previous state-of-the-art.
And that previous best included these massive, complex ensemble models, right?
Exactly. By more than 2 BLEU points. That's a huge leap in that field.
But it wasn't just the score, was it? It was the efficiency gain that really turned heads.
That was the real kicker. English to French, another benchmark. They got a state-of-the-art score, 41.0 BLEU,
Okay.
after training for only 3.5 days on just 8 GPUs, which, compared to the previous model,
It's like a tiny fraction of the compute cost.
a tiny fraction. That combination, better results, way faster training that just signaled everything was about to change.
Okay, so to really get why this was such a big deal, we need to understand the problem they were solving. What was wrong with the old way?
Yeah, let's set the stage. Before
Yeah.
the transformer, it was all about those sequential models, RNNs, LSTMs, GRUs.
So what was the fundamental issue there, the bottleneck?
It boils down to parallelisation, or really, the lack of it. RNNs, by their very nature, compute things sequentially. To figure out the meaning of the third word, the model literally has to process the first word, then the second word, then a third. It's step by step.
Right, like a chain. You can't process word 5 until you've done word 4.
Exactly. So you can't just throw more processors at different parts of the same sentence simultaneously during training. You're stuck waiting for step 2 to finish before you can start step 2 plus 1.
And with long sentences or long documents, that just becomes computationally painful.
A nightmare. Especially in deep learning, where we rely so heavily on GPUs doing lots of calculations in parallel. You're waiting, and the waiting time scales up with the length of the sequence.
So people tried other things, like convolutions.
They did. Models like ConvS2S, ByteNet, they tried using convolutional layers to get some parallelism.
But they had their own issues.
Yeah, they still struggled with long-range dependencies. Connecting two words that were far apart in the sentence still required a number of operations that grew with the distance.
Like linearly or logarithmically, depending on the model.
Right. It wasn't efficient for really long connections. It was like trying to pass a message down a very long line of people.
So the signal gets weaker or takes longer.
Precisely. And the transformer's big goal, the really audacious part, was to make the path length between any two words in the sequence constant. Just one step, essentially.
Wow, okay, constant path length. That's the key. And that required a totally new architecture.
It did. Let's break down the transformer itself. From the outside, kind of looks familiar. It uses an encoder-decoder structure, which is pretty standard for translation tasks.
But inside, it's completely different. No loops, just stacks.
Stacks of identical layers.
Yeah.
And each layer is built from two main parts. Self-attention, and then these simple feed-forward networks.
Let's take the encoder first. It's a stack, you said. 6 layers in the original paper.
Yep, N6 identical layers. Each one has two sublayers. First, a multi-head self-attention mechanism. We'll definitely need to unpack that.
Okay.
And second, a position-wise, fully connected feed-forward network. Simple stuff, really.
But there's some clever engineering gluing it together, right? Residual connections, layer normalization.
Absolutely crucial. Around each of those two sublayers, they add a residual connection and then perform layer normalization.
What's the residual connection doing, like a shortcut?
Exactly like a shortcut. It allows the input to that sublayer to bypass the transformation and be added back to the output. It helps gradients flow during training, especially in deep networks. It stops things from getting lost.
Makes sense. And layer norm helps keep the numbers stable.
Keeps everything in check, yeah. And importantly, all these sublayers and the embeddings, too, they output vectors of the same dimension, DL model 512.2 in the base model. keeps the plumbing consistent.
Gotcha. Okay, so that's the encoder stack. What about the decoder? Also 6 layers.
Also in 6 identical layers,
Mm.
very similar structure, but with one key addition. It has 3 sublayers.
3. So the self-attention and the feed-forward network. What's the extra one?
It inserts a second multi-head attention layer. This one performs attention over the output of the encoder stack.
Ah, okay. So the decoder gets to look back at the original input sentence while it's generating the translation.
Precisely. That's the encoder-decoder attention. It lets the decoder focus on relevant parts of the input sequence for each word it generates. Super important for translation quality.
Makes sense. But there's something special about the decoder's own self-attention, right? Something about masking.
Yes, that's critical for how it learns. The decoder needs to generate the output sequence one word at a time, left to right. So when it's predicting the word at the position I, it should only depend on the words it has already generated, positions less than I.
It shouldn't be allowed to peek ahead at the answer.
Exactly. So the self-attention mechanism in the decoder is masked. It prevents any position from attending to subsequent positions in the output. This maintains what's called the autoregressive property. It learns to predict the next word based on the previous words.
Okay, so the architecture is clean, stacked layers. But the real magic is this attention mechanism. Q, K, V, what's going on there?
All right, let's get into the core function. Attention, in this context, takes 3 inputs: a query Q and a set of key K and value V pairs.
Query, key, value, okay.
Think of it like this. The query is asking a question, like, what information is relevant to me right now? The keys associated with each input element respond, saying, this is how relevant I am to your query.
And the values are the actual information.
The values are the actual information representations. The attention mechanism calculates a score between the query and each key, basically, how well they match.
Like a compatibility score.
Exactly. Then it uses these scores, typically after a softmax function, to create weights. The output is then a weighted sum of all the values. Values corresponding to high-scoring keys get higher weight.
So it's focusing or attending to the most relevant pieces of information based on the query.
That's the essence of it.
Okay.
And the specific type they used is called scaled dot product attention.
Scaled. Why scaled?
Good question. They calculate the scores by taking the dot product between the query Q and each key K. Simple enough. But then they divide that dot product score by the square root of the dimension of the keys.
Score division seems
Yep.
like an extra complication.
It's actually a really clever bit of engineering. They found that for large dimensions DKLers, the dot products could become really large in magnitude.
Okay.
And if you feed very large numbers into the softmax function, it tends to push the probabilities towards either 0 or 1, and the gradients in those regions become tiny, vanishingly small.
Which would stall the learning process.
Right. Learning grinds to a halt. So scaling down the dot products by squared in before the softmax keeps the inputs in a nicer range, maintains healthier gradients, and allows the model to learn effectively. It's a stabilizer.
Oh, okay. That makes sense. A subtle but critical detail. Now, they didn't just use one attention calculation, right? They used multi-head attention.
Yes. This is where the parallelism really shines.
Hmm.
Instead of doing one big attention calculation over the full dimensional vectors,
They split it up.
they split it up. They project the queries, keys, and values into lower dimensions, dWBDVNE multiple times, using different learned projections for each head. In the base paper, they used one attricate heads.
8 parallel attention calculations.
Exactly. Each head performs the scaled dot product attention independently, in parallel. Then the outputs of all the heads are concatenated and projected back to the original model dimension.
Why do that? Why not just one big head? Is it like getting different perspectives?
That's a great analogy. It allows the model to jointly attend to information from different representational subspaces at different positions.
So one head might focus on, say, syntactic relationships, while another focuses on semantic similarity or maybe linking pronouns.
Precisely. If you just had one head, it would have to average all those different types of relationships together, potentially losing nuance. Multiple heads let it capture a richer set of dependencies simultaneously.
Okay, that's powerful. And these attention mechanisms are used in 3 places in the transformer.
Yep, let's quickly recap those.
Go for it.
First, in the encoder self-attention. Here, Q, K, and V all come from the output of the previous encoder layer. Each position in the encoder can attend to all positions in the previous layer of the encoder. Basically, the input sentence looking at itself.
Right. Second.
Second, the masked decoder self-attention. Similar, Q, K, V come from the previous decoder layer, but with that masking applied, so each position can only attend to earlier positions in the decoder output. The translation looking at itself, but only backward.
Got it. And third?
Third is the encoder-decoder attention. Here the queries come from the previous decoder layer, but the keys and values come from the output of the encoder. This is where the decoder looks back at the entire input sentence to help generate the next output word.
Okay, that clarifies the three roles. Now, let's loop back to why they built this whole thing. Speed and efficiency. This constant path length idea.
That outpath length is the game changer. Remember, recurrent layers had a path length of linear in the sequence length.
Meaning the number of steps needed to connect distant words grew with the distance.
Right. Computationally expensive, slow to learn long dependencies.
But with self-attention.
The maximum pass length is $1. Constant. Every word is, in principle, directly connected to every other word through a single attention operation.
That makes learning those long-range connections vastly easier.
Fundamentally easier. And computationally, while the complexity per layer for self-attention is quadratic in sequence length, the number of sequential operations required is constant. Recurrent layers are sequential operations.
So for sequences that aren't massively longer than the model's hidden dimension, self-attention layers can actually be faster to compute than RNNs because of the parallelism?
Exactly. The architecture is optimized for parallel hardware like GPUs. It was built for speed on modern systems.
But wait, if we threw out recurrence and convolutions, those are the things that naturally understand word order. How does the transformer know the cat sat on the mat is different from the mat sat on the cat? Attention itself doesn't care about order, right?
That's a crucial point. The basic self-attention mechanism is permutation invariant. If you shuffle the input words, the attention scores might change, but the mechanism itself doesn't inherently know the original positions.
So they had to add that information back in.
They did. They introduced positional encodings. These are vectors that are added to the input embeddings at the bottom of the encoder and decoder stacks.
So each word gets its normal embedding plus a vector representing its position.
Correct. And they used a clever trick. Fixed sinusoidal functions of different frequencies. So position 1 gets a specific sine-cosine pattern, position 2 gets a slightly different one, and so on.
Why fixed sinusoids? They mentioned they tried learning the positional embeddings too.
They did try learning them, and interestingly, they found it yielded almost identical results to the fixed sinusoidal version.
So why choose the fixed ones?
The authors preferred the fixed version because it might allow the model to generalize to sequence lengths longer than any it encountered during training. The sinusoidal pattern has a structure that can theoretically extend indefinitely.
Neat. Okay, one last architectural piece before the results. Those position-wise feed-forward networks, they come right after the attention in each layer. What are they doing, if attention is all you need?
Yeah, fair question. Think of attention as handling the information mixing and communication between positions. The feed-forward network then processes that information at each position independently.
Ah, like a local processing step.
Exactly. It's just two linear transformations with a ReLU activation in between. Same network applied to each position, but separately. It adds capacity, introduces nonlinearity, and transforms the attention output before it goes to the next layer.
Got it. Attention mixes globally, FFN processes locally. Okay, let's get to the payoff, the benchmarks. Did this elegant theory actually deliver?
Oh, it delivered spectacularly. Back to the WMT 2014 tasks. English to German, the big transformer model they trained hit that 28.4 BLEU score, a new state-of-the-art.
And even the smaller base model.
Even the base model got 27.3 BLEU. That alone beat all previously published models, including the complex ensembles, and it trained vastly faster.
And English to French.
41.0 BLEU for the big model. Again, state-of-the-art, beating all single models published before it. And the kicker was the training cost less than a quarter of the cost of the previous best model.
Just incredible efficiency.
The speed was central. The base model trained in just 12 hours on 8 GPUs back then. The big model, 3.5 days. This wasn't just better, it was faster and cheaper to get better results. That ability to iterate quickly is foundational to why transformers took over.
Did they experiment much with the architecture itself, like the number of heads?
They did. Table 3 in the paper has some interesting ablation studies. They found that varying the number of attention heads, dollars, mattered quite a bit.
What happened?
Well, using just a single head performed significantly worse. That confirms the intuition that multiple heads capturing different subspaces is important.
No way.
But interestingly, they also found that increasing the number of heads too much like 16 or 32 in their tests also hurt performance slightly compared to one antenatal goal for the base model.
So there's a sweet spot.
Seems like it. 8 heads gave a good balance of diverse perspectives without maybe diffusing the focus too much or making the individual head dimensions too small. They also found reducing the key dimension $Hz hurt quality, suggesting that calculating compatibility accurately needs sufficient dimensionality.
Fascinating. Okay, let's wrap this up. What's the big takeaway for you, for the listener?
I mean, the core achievement is undeniable. The transformer was the first sequence model to get top results based entirely on attention. It proved you didn't need recurrence for these complex sequence tasks.
And by ditching recurrence, they smashed that sequential bottleneck.
Absolutely. That unlocked a massive parallelization, leading to faster training, which allowed for bigger models, more data, and ultimately much better performance. This architecture is why we have models like BERT, GPT, everything that followed.
That all or path length really changed the game for handling long sequences. You see models now dealing with huge amounts of text because they can connect distant pieces of information almost instantly.
Exactly. It fundamentally altered the scaling laws.
So here's a final thought to leave you with. The original paper explicitly mentioned looking beyond text. They talked about exploring attention for images, audio, video, maybe using local or restricted attention. Given how attention redefined text, how might scaling these ideas further change how we process massive visual or audio streams? That exploration is still very much happening today.